So the other thing that you can use mass data for is to determine chemical formulas. And specifically what we're talking about is empirical formula, which is the lowest whole number ratio of elements in a compound. So for example, I could have a compound whose molecular formula, so the actual formula is C3H6, its empirical formula would then be CH2, because that's the lowest whole number ratio. And mass data can be used to determine the empirical formula, and then if you can get some more information, you might be able to find the molecular formula. All right? And this information is generally given to you in two ways: as a percentage, like in this problem, or as a mass, as in the next sample problem. Okay? So the way that you go about this, the sort of general outline, is you take percent to mass, okay? Or if you have mass, that's great. Mass to moles, and then mole to mole ratios, because that's what ration. Yeah. How about just ratios? Ratio. Okay, because that's really what a chemical formula is, right? It's a mole ratio. So if you have percentages like this, the first thing that you need to do is you need to get those percentages to masses and then mass to moles. And the way that you're going to do this is you're going to simplify the problem. And the best way to simplify this is assume 100 grams of compound. Okay? That then turns this into a fairly straightforward and doable problem. So I'm just going to do this one, and you'll see what we're doing as we go through. So I've got 36.70% potassium, which means that if I have 100 grams compound, I have 36.70 grams of potassium. So I put grams potassium down here, moles potassium up here. I go on the periodic table, I get the molar mass of potassium, 39.098 grams of potassium. And when I multiply that, I get 0.938667 moles potassium. And I'm not going to round at this point because I have more to do, okay? And I'm going to use these mole values. And the more decimals that you take, the sort of more sensical your answers will be. Okay? So the next one is 33.27 grams chlorine. And I'm going to put grams chlorine down here, moles chlorine up here, 35.45 from the table. And I get 0.938505 moles chlorine. Okay, now you can see that those are roughly 1-to-1. Okay, but it's not exact, right? So your numbers are never going to be exact because this is like data from experiments, and experiments aren't perfect. So you just have to be aware that you're going to get some weird numbers. The last one is oxygen, 30.03 grams oxygen times 1 mole oxygen over 15.999 grams oxygen equals 1.87699 moles oxygen. All right, now you should be able to see that this is a 1-to-1-to-2 ratio, okay? But if it's not straightforward like this one is, which I'll be honest, a lot of them aren't, then what you need to do is you need to divide everything by the smallest number of moles. So this one has the smallest number of moles is 1, right? In the ratio, you hope that the thing with the least number of moles has a subscript of 1. So I'm going to divide everything by the moles of chlorine. So I'm going to take my moles of potassium, 0.938667 moles potassium over my 0.938505 moles Cl. and I get basically 2.0 to 1. And when I do 1.87699 moles oxygen over 0.938505 moles Cl, I get, oh, oops, I did this backwards in my head. That's 1.0 to 1, and this is 2.0 to 1. Okay. So that means that my empirical formula for this compound is going to have a 1 to 1 to 2 ratio. So I'm probably going to put the potassium in front, right? Because that's a metal. So that's KClO2. And that's my empirical formula. Okay? So these problems are kind of steppy, but very doable.